So good day, everybody, and you're welcome to this seminar, the Condensed Matter Physics Seminar of the East African Institute for Fundamental Research. And today we'll be having Dr. Sara Bonella. I'll say a few things about Sara. So Dr. Sara Bonella graduated in physics from the University of Rome La Sapienza. She obtained her PhD from Boston University. She worked with Professor David Coker. After a postdoc at the Scuola Normale Superiore di Pisa, she returned to La Sapienza, where she became a junior member of faculty in 2008. Then in October 2014, she moved to Lausanne to become the deputy director for research at CECAM at EPFL. She has published more than 50 papers in the area of computer modeling of condensed matter systems, and she works in nuclear quantum effects in the description of time-dependent and time-independent phenomena in condensed phase. So more recently, her activity has focused on the development of methods in classical statistical mechanics description of ionic systems under external magnetic fields. And she has developed a new formalism leading to efficient integration of the evolution of systems that have this adiabatic separation. So she's going to talk to us about this new method exactly today. And so we welcome Sara to talk with us about this new method, which they call maze. Okay. So Sara, over to you. Thank you.
Thank you very much. And thank you for inviting me. This is a very nice opportunity for me to meet a new community. And so if you don't mind, I thought that maybe before starting to talk about science, I would tell you a little bit more about the place where I work, which is CECAM, as you heard. And CECAM is something that I think might be interesting for you to know if you're not already familiar with it. Many of you probably are, but I mean, this is a center that was born in 1969 and whose main goal is really to promote collaborative work in the area of simulation and modeling across many, many fields. So materials for sure, but also biology or, continuum physics as opposed to atomistic models. I think it's a fun place to know and to visit. It's had an interesting story. I mean, it was first established in Paris as a single institute due to the proximity with a big HPC center that could be accessed by scientists who were guests at CECAM. And then it moved to Lyon and then to Lausanne in 2008. And then when it moved to Lausanne, it turned from just being a single institute into being a network of 17 nodes. So we have places that are called CECAM nodes scattered across Europe, Israel, and Switzerland. And what we do is we get input from the research community about things that would be fun to discuss at our workshops and schools. And then we also coordinate projects at the European level. We host a visiting program, which is quite active and enables our community at EPFL and across Europe to interact with scientists that come from other parts of the world. And of course, we have institutional collaborations with other organs and organisms that you probably have heard of, such as Psyche, Marvel, and ASESMA. So if you are at all curious about the kind of activities that we run, I would encourage you to have a look at our website, where you will find the full plan of activities for our events, including, and this is particularly important this year and has been incredibly important last year, online events. We do seminars, webinars, and lectures at different levels that you might be curious about. So feel free to visit the CECAM website and to get in touch with me if you want to know more about our activities. Here is just a quick overview of lectures that we have hosted. You can see that, CECAM delivers every 3 years a prize to someone who has made important contributions in the area of development of new methods in simulation and modeling. And then we have talks that go from the quantum and ab initio molecular dynamics to biology, non-equilibrium statistical, classical mechanics. And we also interact with industrial applications and industrial researchers interested in our type of work. So this was then here is an example of our online events. And in particular, I would like to attract your attention on the fact that we do run lecture series, and we try also to create opportunities for younger scientists to get to know us and to be known by the community by presenting in these online events. Again, all this information can be found on the CECAM website. Now, I think that we can move to the science part. I'm happy to take questions during the talk. I saw that there was some movement in the chat. I have to apologize, but it's going to be difficult for me to monitor that. So if you have a question, just interrupt me and we can discuss it. I like things to be as interactive as possible. I am not familiar with the background of many of you, and so it's going to be useful for me if you provide some feedback as I speak, so that we can work together to get to know a little bit of the science that I would like to describe for you today. So this is collaborative work. It's collaborative work that has developed in Lausanne with a couple of very good students that I've been lucky to have, Alessandro Coretti and David Girardier, for some of the most recent stuff. But it's also work that has benefited from long-standing collaborations from scientists in Rome, most notably Giovanni Ciccotti, who was my advisor for my master thesis and with whom I still collaborate, and some very good friends in Paris, Rodolphe Lemieux, Mathieu Salan, and Benjamin Rothenberg. Okay, so I would like to tell you this a little bit as a story, and so to tell you how I started looking into a problem, which was the problem of charge transport of classical ions in the presence of an external magnetic field. And in particular, I was interested in a class of materials called superionic conductors that have the characteristic that they possess a phase in which typically these are two species compounds. In this particular case, it's AgI, which is the prototypical superionic conductor. And AgI has a phase in which the conductivity in the solid state is as high as the conductivity in the molten phase. Now, this is quite unusual. It happens because the I- ions are fixed on lattice positions, whereas silver can diffuse very much as in a liquid freely throughout the lattice. Now, these are interesting materials. And one big question that people ask is, okay, now you have these lightish ion, such as Ag plus in this particular case, that move in a lattice. What happens when you switch on an external magnetic field? Will you be able to observe and measure in experiments effects that are typically associated with electronic conduction? And in particular, people are curious about things like magnetoresistance, but now for ionic transport, or even in the presence of the Hall effect, but the ionic Hall effect. So we started looking into this problem, and we decided that we wanted to look at it using equilibrium simulations. So everything within the framework of classical statistical mechanics, semi-empirical potentials, no DFT for the time being here, and properties like the conductivity in this case, computed from time correlation functions of classical observables. So in this case, the ionic current generated by the motion of the silver ions in the system. And what we saw is, now these are non-trivial calculations for several reasons. We can go into this at some point. But the important thing for us was to see that, yes, we were able to adapt integration algorithms like the velocity Verlet algorithm, for example, typically used to study this type of properties into non-superionic conductors. To this specific case, we were even able to adapt these algorithms to the evolution of the system with the presence of an external magnetic field, which is non-trivial to do. And we could observe, for example, the magnetoresistance of the system, which is described in this figure here, where I show you the diagonal components of the conductivity of the system in the absence of the magnetic field as the black curve. So all diagonal components of this tensor are now equal because the system is isotropic in the absence of a magnetic field. Then we switch on the magnetic field and something rather magical happens. We separate the Z component of the conductivity from the X and Y components of the conductivity. In this case, I have a magnetic field aligned along the Z axis. So I am inducing rotations of the charges in the orthogonal plane, so in the x and y directions. This slows the charge carriers down, which means that the conductivity drops, which also means that I can generate currents that have a certain directionality. Here, for example, the current in the z direction is much larger than the current on the x and y directions. So all this is nice and good, but it turns out that if you really want to be accurate in modeling this type of systems, standard empirical force fields, typically called rigid ions force fields, are not enough. You cannot just treat the ions as point charges, but you need to somehow account for polarization effects. Now, polarization effects for people who do ab initio simulations are easy to capture, in the sense that because we have access directly to the electronic density, so distribution of electronic charge, we can follow the formations of this distribution. And this leads to the polarization effects. But now, if we are trying to model this through empirical potentials, life becomes a bit more difficult, and people have been working for many, many years into the development of polarizable force fields. And the way people do this is they say, okay, I have my ions indicated, whose positions are indicated with the letter R here, and these are the physical degrees of freedom in my system. But I want to add to the physical degrees of freedom of my system some other degrees of freedom, let's call them rho in this case, whose job is to mimic some of the properties of the electronic charge density, but to do so through fully classical variables. So there are many ways to actually try to then play around with these auxiliary variables rho, but all boil down to the definition of an interaction potential between the ions and the ions, between the auxiliary variables and the auxiliary variables, and between the ions and the auxiliary variables. And then, and here you will start seeing where the connection with the ab initio molecular dynamics talk that I promised today in my abstract comes in. Then the physics of the system suggests that because these auxiliary variables represent electrons, they move much faster than the ions, which means that for each ionic configurations, they have time to relax to an equilibrium position in this interaction potential. In other words, the ions, R variables, always move in a potential that is at a minimum with respect to the auxiliary variables. Now you see that this is like a Born-Oppenheimer approximation in which my electrons are always in their ground state, the state where the derivative, where the force is zero, or if you want, the gradient of the potential is zero with respect to these degrees of freedom. And the ions then move on this fake electrons ground state. So the way this type of problems are solved is very reminiscent, and typically, I apologize for forgetting to mention this, but typically the ions move according to Newton's equations. So this is really Born-Oppenheimer molecular dynamics, but not done with an ab initio calculation of the electronic ground state, but done with an empirical calculation of the electronic ground state. But because this is Born-Oppenheimer molecular dynamics, this general problem here that I have rewritten using capital R instead of little r and little s instead of capital S, this is a prototypical problem in adiabatic dynamics. I have timescale separation in the motion of the ionic variables with respect to the electronic type variables, and I move the ionic variables in a potential such that the gradient of the potential with respect to the electronic variables is zero. This general scheme here is the same type of thing that we do when we do first principle or ab initio molecular dynamics. And there are many other type of systems that fall within the category of adiabatic systems. So the kind of things that I am going to describe now that are sort of developed with the ab initio molecular dynamics application in mind can be developed, and this is a little bit simpler from a formal point of view, but within this scheme in which I have classical polarizable variables that I want to use, for example, because I'm interested in superionic conductors. Now, of course, as we know from ab initio molecular dynamics, this type of coupled dynamics between the slow nuclear degrees of freedom and the fast electronic degrees of freedom can be solved using different types of algorithms. There are two main families. One is the class that falls under the general umbrella of Born-Oppenheimer molecular dynamics, in which I do one step of classical propagation of the ions using, for example, velocity Verlet, and then I compute through a nonlinear conjugate gradient minimization the minimum of the electronic energy at those configurations of the ions. So these are the conjugate gradient type of methods. An alternative, and this was the super smart idea that Karen Parinello had in the 80s, is to say, let's not create this artificial separation of variables that I move using molecular dynamics and variables that I only minimize through conjugate gradient, but let's create an extended system in which the ions and the electronic degrees of freedom are all treated as dynamical variables. The ions will have the physical mass associated with them, and the electrons will have a fictitious mass, a fake mass that it's in my hands, and that I choose to be much, much smaller than the ionic mass. And then I simply move the ions and the electronic degrees of freedom together using classical mechanics for everybody. But now, because I have made my electronic degrees of freedom much lighter, their dynamics will be fast compared to the slow dynamics of the ions, and they will sort of automatically, through the dynamics, go towards their minimum energy state, simply because I am reproducing in my numerical experiment the physical conditions that lead to adiabatic separation. Now, both these type of methods have pros and cons. For example, it is known that converging a conjugate gradient minimization in Born-Oppenheimer molecular dynamics can be very costly if I need to achieve high precisions. So if the minimum must be approached very closely, then I need many, many iterations in my conjugate gradient procedure to get there. And this is something that costs money in terms of computational money, of course. On the other hand, if I relax my minimum condition and I don't go very close to the minimum, then the minimization is incomplete. That means that I am not really in the adiabatic regime. And this has problems because the dynamics of the ions gets corrupted. The energy is no longer conserved. I am not exactly time reversible. And this leads to pathologies and the fact that one cannot propagate for very long times in a good way. Similarly, Parinello molecular dynamics has the problem that because I have to follow the evolution of my fast degrees of freedom, I need a very small time step to integrate the evolution equations of the coupled ionic and electronic system. And this is expensive because I need many, many, many steps to follow the dynamics of my fake degrees of freedom, the electrons, when I am interested in the properties of my slow degrees of freedom, the ions. And furthermore, because the mass of the electrons is small, but it's never really zero, I am never fully separated in the adiabaticity of the systems. And then there can be some unphysical energy transfer between the two subsets. And this is also something that creates problems. Because of these known pathologies, there have been more recent methods. I only quote a couple here, the always stable predictor corrector method, also known as second generation Parinello, or the so-called extended Lagrangian Born-Oppenheimer dynamics that have attempted to mitigate some of these problems of the standard methods. They succeed to some extent, but not really. And they all have problems. And in particular, they all fail to really separate the timescales of the two systems, and often need thermostats, so ways to subtract energy from one of the two systems to try to go back towards adiabaticity. And now this is an artificial process that you put on top of your dynamics. So we thought that there was room for improvement, and we started working in this area, creating something called the mass zero constraint dynamics that we claim, but with a big question mark because this is new and so it needs a lot more testing, that it somehow manages this new method to capture the best characteristics of a conjugate gradient and a Parinello molecular dynamics without paying a large price in terms of numerical efficiency. And this is my job for the next of this talk, for the rest of this talk, is going to be able to try to convince you of what I just said. Now, how do we do this? So we do something that looks like Parinello molecular dynamics, because we start by defining an extended Lagrangian for the system where we have the physical degrees of freedom, the ions here, that move with a certain kinetic energy. and interact through our potential, or if you want, energy functional, with the set of the electronic degrees of freedom, the S variables. And to these electronic degrees of freedom, we also assign a finite mass to start and a kinetic energy. So this looks very much like a Carr-Parinello Lagrangian. But then we do one thing that is different from what Carr-Parinello did, and we say that the condition that the derivative of the potential with respect to the electronic degrees of freedom has to be 0, for us is a constraint on the system. So we do classical molecular dynamics, but in the presence of a constraint of a condition that must be strictly respected by the dynamics. So if we derive the evolution equations for this constrained system, moving the R's and the S, we can do this. There are the Euler-Lagrange equations that enable us to do that. And in this Euler-Lagrange equation, there will be one force called the G sub K force, the constraint force, whose job is there to say, okay, you electronic degrees of freedom, you have to be at 0 force, or if you want, this condition must be respected. So these evolution equations here will contain
Sorry, Sarah.
Yes.
Okay. Steve has a question.
Go, Steve.
Can you go back one slide, please? So what is the physical meaning of that constraint? Why do you use that constraint?
So the physical meaning of the constraint is that I want to do Born-Oppenheimer molecular dynamics, right? So Born-Oppenheimer molecular dynamics says the physical degrees of freedom, the R's, move, okay, together with the electronic degrees of freedom, but the electronic degrees of freedom must respect the condition that the derivative of the potential with respect to them is 0, so that they are at a minimum of the interaction potential. Okay?
Okay.
And I am imposing this condition as a constraint on the dynamics of the system.
Okay.
Yeah? So this will, by construction, because there is this force term here that acts to keep my degrees of freedom on the constrained surface, this means that all my degrees of freedom, the ions and the electrons, will move respecting that constraint. So the evolution equations of the system look like this. And you see that here I have mass times the acceleration of the ions is equal to the force acting on the ions minus the derivative of the potential with respect to the ions. And then the ions at this stage feel the constraint force that says, okay, but you ions move with the electronic degrees of freedom at a minimum in the potential. The electronic degrees of freedom have an evolution equation, which is mass times acceleration of them, equal to the force that they experience, plus the force that says you electronic degrees of freedom must be at a minimum of the potential. Now, if I look at this dynamical system here, the first thing that I can observe is that by construction, because this is my condition, this force for the electronic degrees of freedom must be 0, which means that this term is really not present in my dynamical system that I can then rewrite like this. Now let's focus on this equation. All I did is I divided by the mass mu, the evolution equation for the electronic degrees of freedom, that now only feel the force of the constraint, because the other force is 0 by construction. Now I want to do something else that Carr-Parinello didn't do, and I want to really take the limit for this evolution equation when mu, the mass of the auxiliary variables, goes to 0. So no longer a small mass, but a 0 mass. But I want to do this by imposing that the acceleration on my degrees of freedom stays finite, because otherwise I lose the notion of an evolution for these degrees of freedom. Now, the only way that I have to satisfy this condition of finite acceleration is the following. When I send mu to 0, I have to send lambda to 0 in such a way that the ratio lambda over mu remains finite in this limit. I am going to call it gamma. So I do this, and then two things happen. The first one is that I obtain a regular, if you want, evolution equation for the electronic degrees of freedom, where now my constraint force has this parameter gamma, that is the Lagrange multiplier, is the proportionality constant that says how strong the force that the constraint enacts on these degrees of freedom has to be to ensure that they are at the minimum. But then there is another thing that happens, which is super interesting. And this is the fact that in the evolution equation for the ions, because lambda now is going to 0, this force term here that is due to the action of the constraint on the ionic degrees of freedom also vanishes. Which means that if I now look at the evolution equation for the ions, they are moving exactly with a force that it's only the Born-Oppenheimer force. This is the Born-Oppenheimer force because it's the gradient of the potential with respect to the ionic degrees of freedom. And because the S variables that will appear here, because they have to obey the constraint, they will be at the minimum.
Sorry, Rosanna, I don't understand. Why is lambda 0 now?
So lambda is 0 here because I want to send mu to 0 and keep the acceleration S double dot finite, okay? So if mu goes to 0 and lambda is not 0, this thing here will blow because this is, lambda over 0.
Okay.
So in order to keep this finite, I have to send also lambda to 0.
Okay.
But in a way that this limit here remains constant. Okay. This is important.
Yeah. So is it dynamic? Do you change it during the simulation?
Yes. So the problem here, all this scheme here, yes, this is dynamic. All this, so I will have to integrate these evolution equations. Okay. The first one is a standard classical MD type of evolution equation. The second one is also a standard classical evolution equation, right? Because here I have a force, but this force is multiplied by a parameter gamma, which is not known along the trajectory. So I will have to create an algorithm such that I can move my S variables and obtain the value of gamma. Okay. But luckily, this is something that people know how to do, because there is a method that people use in classical mechanics. It's called shake, and it's a method to solve evolution equations for classical systems under constraints. Now, we can discuss this if you want more in detail, but the key point of this slide here is that by using this shake method, I can do the following thing. I can integrate the evolution equation for the nuclear degrees of freedom using any standard integration algorithm, and I can use shake to integrate the evolution equation for the electronic degrees of freedom, right? So that they respect the minimum condition, because I can always find these gammas. Okay. If this is not clear, please stop me, because this is important.
Okay, so shake helps you to find the gamma?
Yes.
Okay, because with shake, you can get the forces that we
precisely.
set. Okay.
Yes, and shake is an iterative way to find these gammas. So in this sense, there is a little bit of Born-Oppenheimer molecular dynamics, because I will have an iterative process, but my iterative process now is this shake method here that I only need to solve for the gammas. And you will see it's very efficient. So we can do this.
Sorry, another question. Is the value of gamma dynamic? Does it change during the simulation? Or?
Yes. So I will have to find gamma for each time step. So here is a scheme, if you want, is a flow chart of my evolutions equation, of my integration algorithm, if you want. So I move my R's from T to T plus delta T using this type of algorithm. Here, this is Verlet, right? So in order to do this, I need the position of R at time T, the position of R at time T minus delta, and the force at time T. The force at time T depends on the nuclear positions at time T and on the value of the S variables here that satisfy the minimum condition at time T. So to do the next step, when I go to T plus 2 delta, right, I will have here forces that depend on R at T plus delta that I have, but also positions for the electronic degrees of freedom that depend on S at T plus delta. The position of S at T plus delta require the knowledge for gamma. To get the gammas, I use shake. So I have the gammas that give me the S at T plus delta, and then I can compute these new forces and advance the ions. At the next step, I will need to solve again now for S at T plus 3 delta, and I will need to find a new gamma. So each time step is I move the ions, I move the electrons and find the gammas, and then I can move the electrons, the ions again.
How expensive is it? How long?
You will see it in a moment.
Okay.
Okay. So the first thing that I wanted to show you is that this is very accurate. So here I am comparing some calculations done using the nonlinear conjugate gradient Born-Oppenheimer molecular dynamics with what we can do using this maze algorithm. This is a G of R for a system of molten sodium chloride. And these are velocity autocorrelation functions and diffusion coefficients. Now the maze algorithm is the lines, and the conjugate gradients is the symbols. So we are exactly where we need to be. Okay, so if we think that conjugate gradient is our benchmark, our reference method, then we are where we need to be. Now about efficiency. Okay. You remember that I told you that things become more expensive for the conjugate gradient, the more strict I am in asking that I am at the minimum, okay? And this is something you can see here. If I say that I accept violations of the minimum condition of order 10 to the minus 3, then the conjugate gradient converges with 8 iterations, and it takes about 1.4 seconds. At this level of precision, the maze algorithm, which is here is called SH for historical reasons, is a little bit, it needs less iterations, but each iteration is a bit more costly, and then it takes the same amount of time. But as I increase my precision, the conjugate gradient becomes much more expensive, both in terms of number of iterations, 74 against 15, and in terms of computing time, than these new algorithm. It takes 12 seconds to converge the minimization using conjugate gradients. It takes 3.6 seconds to converge the minimization using maze, with an absolutely identical level of precision for this type of systems. And this is, you can see it here, this is simply how my electrons go towards the minimum. This is the way they do it using shake. You see, this is a semi-log plot, but basically there is an exponentially fast convergence of the electronic degrees of freedom towards the minimum, which is quite independent, this speed of convergence, from the specific configuration of the ions. The different curves here correspond to different ionic positions for which I do the electronic minimization, whereas the road to the minimum of a conjugate gradient is much, much bumpier. And you see that it takes, on average, 4 times as many iterations to converge for these type of systems. Okay. Now,
sorry, please, let me ask you 2 questions quickly. So, what's this delta E over delta V?
So, delta E is the energy fluctuations, and delta V are the potential fluctuations. So, this is a measure of the accuracy in energy conservation for your system.
Oh, okay. Thanks. So, the other thing is, so you think you can use this for orbitals?
This here is what we have done at the moment. We haven't gone to Constraint yet, but this is the work that we are doing now. But we have done it for orbital free DFT. Now, as you know,
but in orbital free DFT, you don't have to do an orthogonalization, yes, right?
But I didn't discuss it here. But we have tested again on polarizable models that, including the additional conditions like the orthonormality constraint, doesn't break the scheme. And in fact, you know that in standard Constraint, you need n-cube operations to solve the orthogonality. Using maze, you can do it in n square.
Okay.
So that's interesting for this, but we have to test it. Yes. So this is on paper. We haven't tested it in a code. What we did in order to understand how this would work for DFT-based MD is, instead of going to Constraint DFT, we went to this orbital free DFT, in which the energy functional is expressed fully in terms of the electronic density. So we don't go to the Constraint orbitals here, but n is the electronic density of the system. You break the energy functional, as usual, into a kinetic energy, into a pseudopotential, into electrons, and into exchange and correlation, electrostatic interactions, I'm sorry, and into exchange correlation type of functionals. These you get from a standard Constraint type of dynamics. The problem with this type of representation is that getting good representations of the kinetic energy functionals as a functional of the density, not the Constraint orbitals, is complicated. So there is a lot of cooking that goes into that. But there are relatively simple potentials like the ones that I have described here. This one here is called the Thomas Fermi. This is just a free electron gas type of potential, or the von Weizsäcker that adds a GGA type of correction to the Thomas Fermi, or the Perot that adds yet another type of correction to the von Weizsäcker. Or there are more recent non-local kinetic energy potentials that have been used, even though they are difficult. But these type of things are good to describe, for example, metals or metallic systems. So, you know, there is a lot of people, Emily Carter and all her group, for example, that have been working to develop this type of potentials. And more recently, people have been machine learning kinetic energy functionals as a functional of the density and not the Constraint orbital. So there is, you know, a field of applications for this. For us, this was like a first step towards the Constraint idea. And what we do here is we take the electronic density, we expand it, for example, in a plane wave basis set. And then the minimum condition, the Born-Oppenheimer condition here, is that the derivative of the energy functional with respect to the coefficients in this expansion have to be 0. This is the equivalent of the Born-Oppenheimer condition that we had before. We construct a constrained extended dynamical system in which the variables are the ions and the coefficients in this plane basis expansion. And then we propagate using this combination of velocity Verlet for the ions and shake for the electronic coefficients. Okay, so what I am showing here are some results for solid and liquid, maybe only solid in this case, Na or Al, with functionals of increasing complexity. And again, I am comparing nonlinear conjugate gradient minimization here. So this is the path of the electronic coefficients towards the minimum with the maze system, which is here. And as you can see, we find again the fact that the convergence is faster. And it's faster both in number of iterations and in time to convergence, which is what I am showing here. Okay, so in red, you have the time to convergence, the average time to convergence per step of maze, and in blue of the nonlinear conjugate gradient. So this is quite efficient, and it is also accurate. Again, if I compare with conjugate gradient typical observables, the behavior of the temperature of the system or the fluctuations in the energy, in the total energy of the system, I get that when I run maze and conjugate gradient, I get exactly the same results, but maze is much faster. Much faster means that, you know, if I impose a strict convergence criterion, so I admit violations of the order of 10 to the minus 10 in my minimum condition, maze takes on average 0.42 seconds per step with this system, or this was 216 sodium atoms, I think, treated with von Weizsäcker kinetic energy functional. The nonlinear conjugate gradient for the same precision requires 10 times longer. If I try to run the nonlinear conjugate gradient with a time that is comparable to the one that I have to get to 10 to the minus 10, right, then the precision that I can afford on the nonlinear conjugate gradient is only 10 to the minus 1, which means that my minimum is not very good, okay? And when I don't have a very good minimum condition in the nonlinear conjugate gradient, then things start to go wrong. As I mentioned before, energy conservation is very bad. And here, this is something that you can see. Here we have compared, you know, fully converged maze and nonlinear conjugate gradient. And this is the quality of the energy conservation that you get over a 10 picosecond run. But if you run nonlinear conjugate gradient as fast as you can run maze, then the nonlinear conjugate gradient fails to conserve energy. Someone wants to write something? No, okay, I see an orange line on the screen, but I will just keep going. So energy conservation is really, really different if I want to use conjugate gradient and go as fast as I can go with maze. Similarly, this is a bit more intricate as a plot, but this is a measure of the time reversibility of my trajectories. Just get the message that, you know, if I converge fully maze and nonlinear conjugate gradient, I get very good time reversibility. So if I propagate forward my system and then I invert the velocities and I propagate backward, the trajectories are retraced very precisely for very long times. This is the 10 picoseconds. But if I run with the nonlinear conjugate gradient at the precision that goes as fast as maze, then I very quickly get divergence into my forward and backward trajectories. And again, also in the, and the other thing that it's important is that the algorithm that we have implemented for maze maintains the linear scaling of orbital free DFT. So one of the reasons why people like Paul Madden started looking at formulating ab initio molecular dynamics, not a la Constraint, but using orbital free DFT is precisely because in Constraint you have the orthonormality constraint, and that causes your calculation to cost like n cubed, where n is the number of Constraint orbitals. Whereas because if you look directly at the density, you don't have to have orthonormalization of anything. You only have to impose conservation of electrons, but this can be done of the number of electrons, but this can be done very efficiently. Then you can get your algorithms to scale essentially linearly with the size of the system. And what I am demonstrating here, these are calculations done on a single core. So, you know, this is like the first orbital free code that we wrote in my group, but you see that you can go up to 500,000 particles and have something which is pretty much a linear scaling algorithm. So, and again, then you can take this and have a look at observables, and what you get in this case, these calculations had been done using nonlinear conjugate gradient, much longer runs, but you get the same kind of results. This here is the pair distribution function for the system, and these, forget about that, but the red curve here is the diffusion coefficient for this system here when it's molten. So the key message that I wanted to give you is that, okay, this is something very new. He's a very young baby. We have been playing with it for about 3 years now. So I really don't know if and when, and I am sure that we will find that it has many, many problems that we haven't discovered yet. But for the time being, it seems to be an interesting alternative to nonlinear conjugate gradient Born-Oppenheimer molecular dynamics or Carparinello molecular dynamics, because it sort of gives us the good things of both methods, right? From Carparinello, we have these explicit evolution equations for the physical and the auxiliary variables. Here they are, and they all come from a Lagrangian formalism. For us, is a constraint Lagrangian formalism. For Carparinello, the constraints only come in when you do Constraint because of the orthonormality constraint. We use them to impose the minimum condition. One thing that I did not say here is that because the the forces acting on the S variables are determined only by the constraint forces, and because my integration of the role of the constraint forces in this motion happens through shake, not through Verlet, right? Then I don't need a very small time step to integrate this set of evolution equations. And in fact, again, a difference with what happens with Carparinello, I can propagate my system using the time step that is only dictated by the slow nuclear degrees of freedom, just like I do in conjugate gradient. Because I am sending the mass of the auxiliary variables to 0, that means that the adiabatic separation between my ionic and electronic degrees of freedom is exact, which also means that the statistical mechanics that I do is exact because my ions are moving on the Born-Oppenheimer surface for the system. This is also something that it's not easy to guarantee when you are looking at Carparinello molecular dynamics.
Sorry, Sarah, quick question. So setting the gammas, making the gamma equal to 0, is that not too strong? What if you just set the sum equal to 0?
Sorry, the gammas don't go to 0. The mu's go to 0. The mass of the electrons go to 0.
Okay, yeah, you're right. Okay. Yeah.
So the gammas, in fact, are always finite. And you see them change along the trajectory, but they remain. Yeah, exactly.
Okay, now, okay. Sorry. So instead of making the force on each electron coordinate 0, what if you make the net of all the forces 0? Do you think that will?
But then I am imposing a different condition, which is not the one that is usually imposed in Carparinello or Born-Oppenheimer.
Okay, true.
Yeah?
Yep.
So in this sense, I could do it, but then this would not be the same, the physically interesting system that people typically look at.
Okay. Thanks.
Sure. Now,
by how many percent does the gamma change more or less during the propagation?
These I don't really know, but I would say that, so when you initialize the calculation, so when your system of electrons and ions is not even close to where they should be, right? Then you can see that the gammas change a lot. I can show you something, but then as you run, things get progressively more stable, and you sort of see oscillations of the gammas around some values. I wanted to show you something here. These are not exactly the gammas. This is the maximum value of the force acting on the electronic degrees of freedom. And what you may or may not see here is that one of the reasons why maze converges much faster than the conjugate gradient is because whenever I move my ions and then I do the minimization by the nonlinear conjugate gradient, I have to give to the algorithm a first guess on the positions of the electrons from which they minimize. And typically in conjugate gradients, it's difficult to give a good first guess, which means that I start from very high violations, here are of order 10, if you want, of my minimum condition. Another advantage of shake is that because of the way it works, it gives you automatically at successive time steps very good first guesses. And so then we always start, and you can see it also here. Here you see with conjugate gradient, I start from violations that are of order 10. And with maze, I start from violations that are of order 10 to the minus 2. Right? So things don't change too much. And my initial guesses for going towards the minimum are quite good. Does that answer your question?
Yeah.
Okay, cool. So these are, the good things compared to the nonlinear conjugate gradient. I have shown to you that in physically interesting cases, we do have these advantages of strong stability, of good time reversibility, and very good energy conservation. Now, what are the drawbacks of this method? The drawbacks of this method are that here, in order to solve this evolution equation, I need the derivative of my constraint. The constraint is that the force is 0. And so the derivative of this constraint is that the derivative of the force, which means the second derivative of the potential, is 0. So apparently, this algorithm here is dead in the water even before we start, because I don't need only the forces, but I also need the second derivatives of the potential. And these, we know, are things that are expensive to compute, both in semi-empirical models and even more so in ab initio calculations. But from ab initio calculations, we also know that if I have to use the Hessian, so it's not the full matrix that I need, but if I have to take that matrix and multiply it by something, then I can still get good scaling. And this is exactly what happens here. I always have products of the Hessian times vectors. And this is why, as I have shown you, I can achieve linear scaling with the number of degrees of freedom, even if I have to work with Hessians in my game. Now, the other thing that I just wanted to share with you is, okay, so I told you that this is something that we have started playing with quite recently. And here is a bunch of things that we are doing now to keep testing and improving the algorithm. So in the world of empirical models, I told you that I wanted to study superionic conductors in magnetic fields. And this is something that we have done very recently. There is a paper that has just been accepted. But in order to do that, one needs to change a bit the shake that we want to include, because now the constraint condition involves also the velocities of the particles. Charged particles in an external magnetic field feel the Lorentz force. The Lorentz force is proportional to the velocity of the particles. So my total force equals 0 thing now will have the derivative of the potential plus the Lorentz force that has to be set to 0. And this is a technical complication that needs to be addressed when using shake to obtain the constrained motion. But we've worked out a way to do it, and it can be done. You have seen what we are doing with the orbital free DFT. As I told you, this is something that we have been coding on an in-house code. Now we are collaborating with some software developers, and they are creating a GPU version that preserves the linear scaling. This is something that we are doing with the research institute in Genoa. And these will enable us to go towards larger system, even more than 500,000 atoms, as I showed you before, and more complicated energy functionals. Then, as was mentioned in the introduction, I am passionate about including nuclear quantum effects. All that I described here evolves the ionic degrees of freedom using classical molecular dynamics. But we know that many systems, anything that contains hydrogen, even at room temperature, and whenever I go to lower temperatures or higher pressures for my system in materials, for example, then I need to account for the fact that nuclei are also quantum or can manifest quantum effects. For static time-independent properties, there is a reference formalism that enable us to do this, and this is the path integral formalism, and we have incorporated maze into ab initio path integral codes. This is work that has been done by a couple of students of mine in Lausanne. And we are also looking at an even more efficient, although more empirical method that is called the adaptive quantum thermal bath to include nuclear quantum effects in the game. And we are now looking at the phonon spectrum of lithium hydrate as a first test system to see that we can do this, and things are going reasonably well. So maybe in a few months, I'll be able to show you results also for that. The other thing that we are doing, and this is, I think, an important question, is we want to move from orbital free DFT to standard Con-Sham DFT. And this is something for which we have the equations, but we don't have the code yet. But I have a PhD student that is very bright, Taylor Bard, and his job is to actually implement these evolution equations. So I think that that's all I wanted to say. You see here that there is a little Christopher Columbus looking at the horizon. And this is for two reasons. The first one, as I said, this is a new toy for us. So we are exploring other ways in which we can use this notion of constraint dynamics for adiabatically separated systems, also maybe for minimization problems that do not have directly to do with polarization or with ab initio molecular dynamics. But it also means that we are looking for applications that could be enabled by this method, and where this method could be tested even further. I mean, when we get a new toy, it's good to play with it, but really what we want to do is we want to see how much we can play with it before we break it. So we are really exploring at the moment the landscape to find what are the limitations of this method. I mean, I can tell you a couple. The Hessian is a problem, for example. But for the time being, these have not proved fatal to us. So if you have anything that you would like to suggest as a benchmark system or a test system, I am very interested in discussing this with you. Other than that, thank you very much for your attention, and ready to take more questions if you have them.
Thank you very much, Sarah. So we take questions. Yeah, go ahead. Steve.
Yes, Sarah, I have some, it's a little bit silly, but the S coordinate, what does it actually represent properly? Is it Cartesian coordinate of an electron? What is it exactly?
Okay, so this depends on the system and in the application. In the polarizable model that I showed you, this one here, okay, then yes, rho, which is our S in the following slides, I apologize for the notational confusion, but it is, if you want, the coordinate of a fictitious electron. Here I am trying to model dipolar effects. So I have my ion, mass M, charge Q, position R, and I want to have a negative charge that it's bound to it and that will sort of move around, oscillate around my physical charge to represent, if you want, the motion of the center of mass of the electronic distribution around that atom. So here, yes, in this particular case, for this empirical model of polarization, the auxiliary variable morally is the coordinate of an electron. But then here, when I go to orbital free DFT, right, I didn't write the explicit evolution equations, but the degree of freedom, the auxiliary degree of freedom that I put in the game is the coefficient in the plane wave expansion of my electronic density. You know, when you do Carparinello Consham DFT, right? The Lagrangian that you write has the evolution equations, and then it has the electronic orbitals as degrees of freedom. And then you expand these electronic orbitals in a basis, and the coefficients of these expansion of the electronic orbitals are your auxiliary Carparinello variables, right? So for us here, this is the same. So our electronic degrees of freedom here are the expansion coefficients. So the nature of the auxiliary degrees of freedom changes depending on the system, but the structure of the dynamical system doesn't.
Okay, something else. So the way the method is constructed is meant to study only, you say adiabatic effect, but it's more or less ground state effects. Is there any way you can incorporate non-adiabatic effects?
So non-adiabatic, so this is a great question, and non-adiabatic effects are a passion of mine. I have been studying them with many different methods, including, you know, semi-classical molecular dynamics, including path integral based methods, including surface hopping type of things. You could do a surface hopping type of propagation using these type of schemes. The issue that I still haven't worked around, but this is something that I plan to investigate in the future, is that, of course, one of the key problems of non-adiabatic effects is that they break the adiabatic condition, right? Yeah. So at some point, this idea of full separation of the timescales of the motion when you have transitions between electronic states is violated, okay? And so one needs to adapt this method to do that. So surface hopping, I think I could do it straightforwardly, because surface hopping, you know, is, you know, move adiabatically and then ask, do you hop or not? If you hop, move adiabatically on another surface. And this we can do using this scheme. But now if I want to have the real, if you want, non-adiabatic evolution of my electronic degrees of freedom, that requires a bit of thinking.
Okay, thank you.
Mm-hmm.
Okay. Other questions? So, this is not a question. So, Sarah, so you think one thing one could do is, because you're doing MD, then you probably don't have to do the shake at every step. Is this possible? Like maybe because the
so what you're saying is,
yeah, the gammas will still remain more or less the same as the previous step, and then you just use that for a few steps before you do the update.
So this is interesting, and it's something that we will be looking into. It's a little bit dangerous, because if you don't have the exact gammas at each time step, you don't have the exact minimum at each time step. And that means that you have small violations of your adiabatic condition at each time step. And these small violations have the horrible habit that they build up, they accumulate. And so at some point, you will break the system. Now, what one could think about doing is sort of keep more or less the same gammas for a few steps. So you do 10 steps without doing shake, and then you redo shake.
Okay.
But to be honest, because the method is not particularly expensive in the domain of these methods, I am not sure that we will need to do it.
Okay.
But it's an interesting idea, yes.
Okay, what about say to use this S variable as a thermostat? So in that case, would you set ds to 0, or what will you do? For instance, say there's a Hoover thermostat.
Yes.
So okay.
Right. So that this is a great question that enables me to give you a sort of a preamble and then the true answer to your question. A lot of the methods that are around, the nonlinear conjugate gradient, the second generation Carparinello, the extended Born-Oppenheimer Lagrangian methods, or Lagrangian Born-Oppenheimer methods, they all introduce thermostats sort of to correct violations in the adiabatic condition. Okay. But in doing so, and even Carparinello does that. Sometimes you thermostat the electronic degrees of freedom when you see that there is energy exchange between those degrees of freedom and the ions. But when you do that, then you are somehow corrupting the dynamics. So if you want to propagate constant energy dynamics, right, then you want to have the exact energy of one system and the exact energy of the other system without quenching energy exchanges. Because of that, when you thermostat, you no longer know exactly what statistical ensemble you are sampling. And so this is a problem. Now, a different question, and I think this was your question, is what happens if you don't want to propagate constant energy, but you want to propagate constant temperature for the ions?
Yeah, or sample the canonical ensemble.
Exactly. And then the answer is you do Langevin or you do Nosé-Hoover dynamics for the ions, and you do exactly what I just showed you for the electrons. Because the system that you want to keep at constant temperature is the system of ions, right? Yeah. And the system of ions will move to with a deterministic force and the thermostat. The deterministic force is exactly the same Born-Oppenheimer force that we are looking at now. So for that part of the calculation, you don't need to modify anything. In fact, we have done it, and what I was sort of hiding before, but I can show you maybe quickly now. Here, this plot of the diffusion coefficients here, you see that there is a gamma equals 0, a gamma 10.5, gamma 10.2. Gamma equals 0 is NVE dynamics, or if you want, is a Langevin thermostat with 0 friction. And then these are Langevin thermostats with larger and larger friction parameters. And what you see, done exactly like I described to you right now. And what you see is when you have a lot of friction, you kill the dynamical properties of your system. But as you make the friction smaller, you approach the correct dynamical properties in the NVE ensemble. Yeah. So and the same thing is true for barostats and blah blah. So you can use Nosé-Hoover or Parinello-Raman dynamics for the ions. When you compute the ionic force, you do it using maze.
Okay. Thank you very much. Okay.
You are very welcome.
Yeah. Do you have any other questions? So Sarah, someone is asking if you could share your slides.
Of course, yes. Shall I send them to you?
Yeah, you can send it to me and then I'll distribute it to Steve will put it in, you have a drive and people can access it from there.
Okay.
Yeah. And then also we'll put the video online on YouTube. Okay. So Ange, do you want to unmute yourself and ask the question? Sorry, Bernice. Oh, I said Ange. Do you want to unmute yourself and ask the question? There's a question in the chat.
I see it, but it's nicer if the person asks it, or shall I just read it? Also, because I am not sure I understand the question.
Yeah, me neither. Bernice, do you want to unmute yourself and ask? Okay, so Bernice is one of our master students. Okay, her network is not good.
Okay.
She's one of our master students and she is in the first year. So she wants to know how this method is related to the statistical approach of adiabatic system. So when you say adiabatic, how is it related to when we say adiabatic in statistical mechanics?
Okay, so okay. So I think when we say adiabatic in statistical mechanics, we think about systems that do not exchange energy with one another. Correct me if I am wrong or if this is not the meaning of your question. Now, in this sense, this is exactly an adiabatic system in the following sense. We have nuclei that have a certain energy, and we have electrons that always have an energy that it's a minimum. but we don't want the energy to transfer from the nuclei to the electrons. So we don't want the nuclear motion to excite, to warm up, if you want, the electrons. And we don't want the electrons to give energy to the nuclei. So this is, in fact, an algorithm that by construction enforces strict zero energy transfer between the electronic and the ionic degrees of freedom in the system. So I hope that this is, it does exactly that. It is exactly that.
Yeah, this is perfect. Thank you very much, Sarah.
A pleasure.
Okay. So if there are no more questions, then we thank Sarah for the very good talk. And then also, we'll remember to take a look at the second website. Try to attend as many workshops for our research as possible at the second website. Yeah. So thanks a lot, Sarah.
Thank you, and Steve in particular for the questions that you asked throughout the talk. But thank you very much for this kind invitation. And do not hesitate to get in touch if you have curiosities both about CECAM and about this method. I'll be happy to exchange.
Yeah, definitely. Yeah. Thank you very much. Yeah.
Very good.
Thank you
Guys. Bye. Have a good afternoon.
Yeah.
Bye.